Ever wonder what stops your office network or even your home network from just collapsing into a chaotic mess of data every single day? Well, it's not magic. It's a protocol, a set of rules that's been quietly guarding against network meltdowns for decades. And today we're going to pull back the curtain on this unsung hero, the Spanning Tree Protocol.
So here's a weird thought for you. In almost every part of life, backups are a good thing, right? A spare tire, a backup generator. But in networking, adding just one extra backup cable between two switches can be the very thing that brings the entire network to a screeching halt. How is that even possible? Well, that's the paradox we're here to unravel.
All right, here's the game plan. We'll start with the problem itself, the danger of network loops. Then, we'll introduce the really elegant solution designed to fix it. We'll get into how it cleverly elects a boss to keep order, and see how it evolved from slow to super fast. And finally, we'll ask the big question. Where does Spanning Tree even fit in the crazy fast networks we have today?
Okay, let's dive right into the problem. Adding an extra cable between your network switches for a backup, it just seems like a no-brainer. If one link fails, hey, the other one takes over. Simple, right? The issue is, without some kind of traffic cop directing the flow, that one smart move can create an absolute network-wide catastrophe.
And the villain of our story is something called a broadcast storm. Just imagine one computer asking a really simple question to the whole network, like, hey, who has this IP address? Well, with a loop, switch A forwards it to switch B. Switch B sees it and sends it right back to A. A sends it back to B, and this just repeats infinitely at lightning speed until the entire network becomes this screaming whirlwind of the exact same message, drowning out literally everything else.
The side effects are absolutely devastating. The network literally drowns in its own traffic. The switches get completely confused. Their internal address books, the tables that tell them where every device is, are constantly being rewritten with bad info. Their processors just overload, and none of your actual important traffic can get through. It's a total system failure, all from one extra cable. So how do you get the benefit of having that backup cable without causing all this chaos? Well, thankfully, some very smart engineers came up with a really elegant solution, a protocol designed specifically to tame this storm before it can even begin. And here is our hero, the Spanning Tree Protocol, or STP, invented by the brilliant Radia Perlman. And the concept is so simple yet so powerful. Instead of letting the network be this messy web of connections, STP imposes order. It creates a single, logical, loop-free path, kind of like a tree with all these clear branches, but absolutely no circles.
And here's exactly how it works. On the left, you see the problem. A physical loop where data can circle forever. On the right, you see the solution. STP just logically blocks one of the ports. Now, it doesn't unplug the cable, it just turns that link into a standby path. So the loop is broken, but that backup path is sitting right there, ready to be activated the instant the main one fails. Pretty clever, right?
Okay, this all sounds great in theory, but how do a bunch of separate machines actually coordinate all of this? I mean, they can't just have a meeting and chat about it. They need a system. An algorithm. Basically, they need to elect a boss.
STP's master plan is actually pretty straightforward. It's got 3 steps. First, all the switches hold an election to pick one root bridge that's going to act as the main reference point for the whole network. Step 2, every other switch calculates its single, best, most efficient path back to that root bridge. And finally, and this is the magic part, any link that isn't part of one of those best paths gets put into a blocking state. And just like that, no more loops.
But that leads to the really obvious question, doesn't it? In a world of machines, what does an election even look like? I mean, there are no campaign speeches, no ballots. The decision has to be made automatically and consistently every single time.
Well, the answer is something called the Bridge ID, or BID. You can think of it like a unique name tag for each switch. It's made of 2 parts, a priority number that an administrator can set, and the switch's own unique MAC address. Think of it like a hardware serial number. And the rule for the election? It's dead simple. The switch with the lowest overall bridge ID wins. Period. That's how you become the root bridge. Let's look at a quick example. So here we have switch A and switch B. Both have the default priority of 32,768. So that's a tie. The election then moves on to the tiebreaker, the MAC address. And since switch A's MAC address is numerically lower than switch B's, it wins the election. Simple as that. Switch A becomes our root bridge. It's totally deterministic every single time. Now, the original Spanning Tree Protocol was a total game changer.
But it had one really big flaw, and that flaw became more and more obvious as our networks got faster and more critical. It was slow, like painfully slow.
How slow are we talking? Try 30 to 50 seconds. Seriously. Imagine a link failing and your entire network just stops for almost a minute while STP slowly figures out the new layout. In today's world, that is an absolute eternity. That's a dropped video call, a failed credit card transaction. It just wasn't good enough anymore.
So the protocol needed a serious upgrade, and the answer was the Rapid Spanning Tree Protocol, or RSTP. It completely slashed that 30 to 50-second recovery time. We're talking down to under 6 seconds, and honestly, a lot of the time it's just milliseconds. It was a true night and day difference for network stability.
So how is it so much faster? Well, what's the secret sauce? Instead of just sitting around waiting for slow timers to expire, RSTP switches proactively talk to each other to negotiate any changes. But even more importantly, it introduced these new alternate and backup port roles. And what that means is that every switch already knows its plan B before a failure even happens. So it doesn't have to waste precious seconds figuring things out from scratch when a link goes down.
RSTP was a huge leap forward, for sure. But you know how it is with technology, it never, ever stands still. And even with all its speed improvements, the fundamental approach of Spanning Tree, blocking links, has some real drawbacks in the massive, hyperscale networks we rely on today.
See, STP's core strategy is to block links to prevent loops. But that means those expensive, high-capacity fiber links you paid for might just be sitting there, idle, doing nothing, just waiting for a failure. That's wasted bandwidth, and that's wasted money. Plus, for some supercritical applications, even the few seconds that RSTP might take to recover is just too long. And these disadvantages, of course, led to new technologies. Things like link aggregation let you bundle multiple cables into one giant logical connection, so you can use all the bandwidth all the time. Other designs just handle redundancy at a higher network layer using IP routing, which is inherently loop-free by its very nature. And then you have newer protocols like shortest path bridging, designed from the ground up to use every available path, completely eliminating the need to block links at all.
And this quote right here, it captures the modern reality perfectly. STP is no longer the star player for providing those backup paths. That job now belongs to more efficient technologies. Instead, it's become a safety net. It just runs quietly in the background like a last line of defense, just in case someone accidentally plugs a cable into the wrong port and creates a loop. It's there to save us from ourselves.
So, this leaves us with one final big question. With all these powerful new protocols that can use every single link and provide almost instant failover, has the Spanning Tree Protocol finally served its purpose? Even in its faster, rapid form, is it maybe time to finally retire this old guardian of the network for good?